Alright, we're going to continue section 14.8 in this video, and we're on page 968, and we're going to do number 24. Alright, so number 24. So in exercises 18 through 25, evaluate the integral by a suitable change of variables. So for some of the exercises in the textbook, they give you what change of variables to use. So like we've been given the change of variables to use for polar coordinates, cylindrical coordinates, spherical coordinates. But for 24 and these problems, they don't give us a change of variable. We have to figure out the change of variable either from the region that we sketch or from the integrand or a combination of the two. So 24, we're told to evaluate the double integral over r of x minus y quantity squared times sine squared of x plus y dA, where r is the region bounded by the parallelogram with vertices pi 0, 2 pi, 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 2 pi, and 0 pi. Alright, so now in the steps that are given as to how to approach these problems in your textbook, the first step is to define the transformation. But before we do that, remember I've told you all you always want to sketch your region. So same thing applies here for a double integral. We want to sketch the region that we have, and that's how we're going to define our transformation. So we are only in the first quadrant. So let's and they give us 4 points. They give us pi, 0. They give us 2 pi, pi. So this is not going to be drawn to scale, but pi. And let's put 2 pi right here. So that was the first point. The second point they gave us. And then pi, 2 pi. So we're going to put 2 pi all the way up here. And lastly, 0 pi. Alright, so this is the parallelogram formed by those points. And my scale is off terribly, but that's okay. Alright, so this is the region R. So the first step in the procedure that is on page something in your book, on page 963, was to define a transformation from R into the UV plane. Oh, and actually in that they mentioned for this you will need to use your knowledge of R and perhaps the integrand. So they say we would need to use our knowledge of R, and we may also need to use the integrand of the function that we were given in the first place. So let's write out some stuff let's figure out what all of these equations are for these lines. So we look at this and we see it's neither a type 1 nor a type 2 region. If we wanted to split it up, we could split it up into some separate regions and then define it as either type 1 or type 2 and then do two integrals. But this is an issue, but the bigger issue actually ends up being this integrand, because even if we split this up, trying to evaluate this integral will probably be a mess. So both our integrand are posing us, both the integrand and the region are posing us a bit of an issue. So we're going to look at this in conjunction with that and see if we can simplify things. So this line right here between 2 pi and pi and pi, 2 pi, that will be the line. If possible, we want to write this stuff in terms of like either that or that. So this will be the line y equals negative x plus 3 pi, So that's the same as x plus y equals 3 pi. And then this will be, I'm just using the 2 points that we have. So you can take the 2 points, find the slope, and then from there you can use the point slope formula to find the equation of the line. but I'm rewriting instead of y equals, writing it that way if we can. Now this line over here is going to be y equals x plus pi. So that's the same as x minus y equals negative pi. So this is x minus y equals negative pi. This line here is, this is y equals negative x plus pi. So that's x plus y equals pi. And then over here, this is y equals x minus pi, which is x minus y equals negative pi. X minus y equals negative pi. So now we've written all four of these lines kind of in the same terms that our integral was, in the same terms of functions we see in our integral. So now we can do step one of the procedure. Step one of the procedure said to define the transformation, we're going to let u be equal to x minus y. And notice what we'll end up being able to do is substitute that u in there. And we can also find bounds for u from these two equations we have right here. Do I have these equations certainly can't be the same thing. So this one was supposed to be x minus y equals negative pi, and this one was supposed to be x, the y-intercept's negative pi. So this should have been, I moved that, so that should be positive pi right there. So make that one positive pi because my y-intercept here is negative pi. But I messed up my signs there initially. All right, let me make sure I have the rest of these right. 3 pi and okay. All right, so we're going to let u be equal to x minus y because we see that there, we see that there, and we see it there. And we're going to let v be equal to x plus y. All right, so now we defined our transformation, and then the next thing we want to do is we want to find the bounds on u and v based upon what we have up here. So the fact that we have, say, we'll look at x plus y equals pi. So x plus y equals pi. What does that say for us? Well, that just tells us v equals pi. And then what do we get from x plus y equals 3 pi? That gives us v equals, and remember these are variables, so I'm not saying that pi equals 3 pi. We're finding bounds on v. And then y, x minus y equals negative pi. X minus y equals negative pi. That gives us u equals negative pi. And x minus y equals pi gives us u equals pi. So now we have bounds for u and v. V goes from constant to constant, and it goes from pi to 3 pi. And u goes from constant to constant, and it goes from negative pi to pi. So now instead of sketching the xy plane, we're going to sketch in the uv plane. So this is one thing that we never did when we were doing polar coordinates, spherical coordinates, and cylindrical coordinates. We always sketched everything in the xy plane. But now we're going to kind of get an idea as to why those change of variables made things easier, because we're going to see what this region looks like in the UV plane versus what that region looked like. So the convention is that the horizontal axis is the letter that's closer to the front of the alphabet, so or the beginning of the alphabet. So here we're going from negative pi to pi on the U. So we'll make this U. and we make this v. Now, it doesn't matter if you don't use this convention, because when you set up your integral, everything's still going to be aligned fine. You'll get your answer correct regardless. So we're supposed to be going from negative pi to pi here. My scale is going to be off again. And we're supposed to be going from pi to 3 pi. So we'll put 3 pi right here. And we'll put pi right here. So now we end up with this rectangle. And this is our region S. And this is a lot nicer, a region over which to integrate, than is that region that we had up there. So this is step 2 of that procedure that we were going through. So that was step 1, that's step 2. Now step 3, I tend to always do step 3 of that procedure, which is to take this system of equations and solve it for x and y. I'm not going to do it just so you all can see some instances where you don't have to do it. I tend to always do it because I like to have what x and y are equal to, as well as what u and v are equal to. But I'm going to show you that we can skip that in this problem. You can't skip that in all problems. So I'll show you in another problem where we can't avoid solving this system for x and y. So we're going to skip 3, but I'll show you why we can skip 3. So step 4 is, so the Jacobian says usually we need to find the partial of x with respect to u and v and the partials of y with respect to u and v. So that's another reason we would want to solve this system for x and y, to find the Jacobian. But if you already have u and v, there's another formulation that you can use, which is the Jacobian is 1 over, so 1 divided by So this is the Jacobian of j of uv. This, on the other hand, that I'm putting down here, the denominator, is j of xy. So you can, when you need this, you can use this if you already have your system that way. So if you have u and v, you're always going to need this for your integrand every single time. But if you don't want to solve this system for x and y, you can do 1 over this. Now, what is this, though? We haven't seen that. So that's equal to 1 over. So this is going to be the partial of u with respect to x u with respect to y, partial u with respect to y, sorry. The partial of v with respect to x, and the partial of v with respect to y. The determinant of that. So now we can easily compute those partials from right here. So we end up with this is equal to 1 over the partial of u with respect to x is 1. The partial of u with respect to y is negative 1. The partial of v with respect to x is 1. And the partial of v with respect to y is 1. So this is equal to 1 over 1 and then minus the negative 1. So that gives us 2. So that's our Jacobian. So now, so we can do this, or what we could have done instead, I'll squeeze that over here. So, or if you don't want to use this reciprocal approach. Solve the system for 3. Solve the system u equals x minus y, v equals x plus y for xy, and then find Jacobian. So that's an alternative, is that you could solve that system and then do it the way it was actually defined in the lecture notes. All right, so now we have everything we need to piece together our integral. We have the region over which we're integrating, that's S, with, of course, the bounds that correspond with that. That's the key thing that we need. We have our Jacobian. The Jacobian for us is it's that factor that's in the integrand. For polar coordinates, the Jacobian is R. For cylindrical coordinates, the Jacobian is R. For spherical coordinates, the Jacobian is rho squared sine phi. So we're finding that Jacobian for whatever the particular change of variables problem it is that we're doing. In this case, it happens to be 1/2. Don't forget that in your integrand, you always have to do the absolute value of whatever your Jacobian is. So had this been negative 1/2, for instance, then we need to make sure in our Jacobian we put in positive 1/2, the absolute value of whatever it is we get. All right, so now we're ready to go ahead and set up our integral. And we end up with, so our original integral, let me write that down. First, the double integral over R of x minus y, quantity squared, times sine squared of x plus y dA. Now equals the iterated integral, but now over S. So we had u went from negative pi to pi, and v went from pi to 3 pi. Now we want everything in terms of u and v. X minus y is just u, so that, I think that was u. Where's that v? Yes, that was u, so that's just u squared. And then sine squared of x plus y was v. And then times our Jacobian, so don't forget about your Jacobian, 1/2. And these were v's, so that's dv. And these were u's, so that's du. And now this integral is much more manageable than that last integral we had here. Actually, you can, because these are all constants, and you can split this up into a function of u times a function of v. We can use this approach and rewrite this as, oops, I left off my negative 1/2, so I'll put it somewhere. So the integral from negative pi to pi, and those were u's of u squared du times the integral, the 1/2 over here, from pi to 3 pi of sine squared of v dv. Remember, you can only do this when all of your bounds are constants, and you can split up your integrand into a product of functions of each one of your variables, and then you can split that up and evaluate it that way instead. All right, I'm gonna stop this video here, and then we'll continue with another example from 14.8 in our next video.